Plan for today. Questions here about related to the test.
I have a question. I can get to them. Alrighty. Could you do this? I had trouble with number 7 on worksheet 4.
What's the good word, my bird?
Someone is actually going to take them who's going on the trip.
Oh. Okay. You said number 7?
Yeah.
All right. So we always start from the inside out. So arc sine of 2x plus 1 means I'm going to imagine I have a right triangle. I'm going to designate an angle theta. And then opposite that angle theta has to be my side 2x plus 1 over the hypotenuse, which is 1. So using the Pythagorean theorem, I can say 2x plus 1 squared plus 1 squared is equal, plus b squared is equal to c squared, where this is b. So I FOIL this out. I have 4x squared plus 4x plus 1. Oops, that should be 1 squared. Plus b squared is equal to 1. I move everything over. I square root both sides. I can drop the plus or minus because it's a side length of a triangle, so it's fine. And then cotangent is adjacent over opposite. So that's going to be that negative 4x squared minus 4x square rooted all over 2x plus 1. And did we do some other weird simplifying here? Let's take a quick look. Oh, I just screwed up the key. Because look what I did. I put these in the wrong spot, right?
Yeah, I was going to say.
Oh, arc. Well, I had arc cosecant in the problem. What does our problem say? Oh, well, that's
I
why.
was going to say, I think you did arc sine.
Yeah, I did arc sine. How come you didn't stop me earlier?
It's like I was trying to see what you did, and
Well,
usually you're not wrong. Usually I am. So
doesn't mean that it can't happen.
that's true. I just wanted to see you do extra work then. We'll change that. No, I'm kidding.
So there's that.
Okay. Sorry about that. Okay. Did you have to foil it?
I foiled out 2x plus 1 squared, because that's how you multiply. Right? Same thing that we did before, just everything's just in a little different place.
Okay.
And then cotangent is adjacent over opposite. And if I notice here that there's a greatest common factor of 4, right? So I can break that as like at the multiplication symbol to do that. So there's the 2.
Okay.
And then it's root x squared plus x. I think that's as good as you can do.
So when it's like x plus a number, then you always FOIL it if you.
So, well, the definition of multiplication or of an exponent is repeated multiplication, right?
Yeah. Okay.
It's what you have to do.
Okay. I understand.
Sure. Who is next? Mackenzie? 26 from the problems. Okie dokie. Pick the right problems though, right? We shouldn't be doing chapter 5 problems yet. All right. You said 26? Okay. Okay, so this says a boat leaves the port going 160-degree bearing, 38 knots for an hour and a half, then turns to 75-degree bearing, travels 50 knots for 3 hours, then turns again to 285 bearing, travels 40 knots for 2 hours. What's the boat's distance and bearing from the origin? So this really has 3 legs to our trip, right? So I'm going to break this up into 3 separate components. So 160 degrees is like here. So the theta there is going to be this one, which is 270 plus 20, so 290. And we're going 38 knots for an hour and a half. So 38 times 1.5 is plus 19 is 57. The next one, we're going 75. So my theta there is just going to be 15. And 50 knots for 3 hours, so that's 150. And then the last one, bearing of 285, so we're up here. So our theta in that case is going to be 165. Mackenzie, is everything going okay so far? Okay, 40 knots for 2 hours is 80. So our x1 is going to be 57 cosine 290. And our y1 is going to be 57 sine 290. Our x2 is going to be 150 cosine 15. And our y2 is 150 sine 15. Oh, thanks. And then x3 is going to be 80 cosine 165. Y3 is going to be 80 sine 165. And then our final position is just going to be the sum of these x's and then the sum of the y's. So far, so good, Mac? Okay, let's type that all that mumbo jumbo into our calculator. Got to check here first to make sure I'm in degree mode, because all of our angles were in degrees. So we got to do that. So 57 cosine, 290 plus 150 cosine 15 plus 80 cosine 165. So that's 87.11. And then just replace all the cosines with sines. And we got 5.97. That so far so good? Okay. My distance, my final distance then is just going to be the Pythagorean theorem on those guys. Oops. So I get 87.31. And the distance there is nautical miles. And then the bearing, is that the other thing it asks for? Yeah. So if I plot that, we're going 87 over and 5 up. So that's our bearing. So my bearing there is going to be 90 minus alpha. Oops. Where the alpha is going to be the tan inverse of the absolute value of the y final divided by the x final. So 90 minus tan inverse y divided by x. Notice I didn't worry about the absolute value because everything was positive anyways. So I get about 86.09. Oops, shouldn't put it there though, because it's not alpha. What'd you think? That's okay? Did that match what the answer is supposed to be? Oh, this was an even one? Oh, because of the third turn? Because there's 3? Okay. So if there was 10, would you know what to do? Yes. Okay. No big deal. I'm just wanting to make sure, because I was trying to figure out what we're asking about. Hold on, let me read it real quick. You would use like 2/3 of an hour and half an hour, because knots are in nautical miles per hour. So if you wanted the distance, you need to multiply it by hours and not minutes. So it's just like a little unit conversion on top of, but nothing substantial. Yeah, no problem. Ooh. Huh? Oh. Who's next? Do that. Mackenzie. Third page, letter E. Okay. So first thing that I'm going to do is I'm going to work from the inside. Oops. So I'm going to evaluate tangent of 5 pi over 4. So I'll go to my unit circle. Oops, that's down at the bottom. I find 5 pi over 4. I know tangent is y over x. So that's just 1. Then I'm going to remember that my range for arc cosine or cosine inverse goes from 0 to pi. So I'm going to go back to the unit circle and look for the place where the x coordinate is 1 inside that range. So if I go back to my unit circle, the place where the x coordinate is 1 is right here at 0 radians. So the answer there is just 0.
Wait, so it just has to be any point that's 1 in the x spot?
Well, it's not any point. It's the only point
The only point, okay.
where x was 1
Okay.
on the interval from 0 to pi.
Gotcha.
There should only be one spot
Okay.
on any of these because we define the ranges to be just so.
Gotcha.
Grace. 6 from worksheet 3. Shoot. Yes, of course. Okay, you place a giant balloon animal in the front of your friend's house. That's so nice of you. To ensure that it does not blow away, you tie 2 cables to the top of the balloon and secure the cables to the ground on opposite sides of the balloon. If the 2 cables are attached to the ground exactly 37 feet apart from one another, and the cables form 55 and 62 degree angles with the ground, how tall is the balloon? So this is our picture, right? Happy with what we've drawn? Okay. So, quick question. Can I just split 37 in half and put half on one side of the height and half on the other side? No, why not?
It doesn't say it's 55 and 62 degrees, so it's different.
Great, because it's not an isosceles triangle, right? If those 2 angles were the same, then yes, you could do that. Those 2 angles are different, so no, you cannot. Everybody good with that? So what we'll do is I'm going to call this side x and this side 37 minus x, or you could do it vice versa. It doesn't really matter. And I'm going to create a system of equations and solve using each of the 2 triangles. So I'm going to do one equation for that triangle and then one equation for that triangle. So I can say tan 55 is equal to opposite over adjacent. And then tan 62 is equal to opposite over adjacent. So far, so good. Okay. I'm going to then multiply both sides of the first equation by x. And multiply both equations, or sides of the second equation, by 37 minus x. Cool there. I notice both of these are equal to h, so I can set them equal to each other. That gets me down to one equation with one variable. We'll distribute the tan 62 through, and then move the x's onto one side. Is that okay? On the left-hand side, I notice both of them have a factor of x, so if I factor that out, I can then divide both sides by tan 55 plus tan 62. And then it's calculator time. Note that I'm not looking to solve for x, though. I want h, but I need to get that value for x as an intermediary. This is going to be rather complicated type in my calculator, so I'm going to use the fraction command to make sure that I don't like goof up any parentheses, because there's going to be potentially a lot of parentheses in there, and it just heck of a lot easier to just be able to type it in my calculator the way it looks on my sheet of paper. So that's my answer for x. But I don't want x, I want h. So I'm going to use that equation to solve for h. So I can just multiply that value of x by tan 55. So my h should be about 30.0 feet. Is that cool? Sure. Again, pretty similar to the ones that we had done in the example, right? At least algebraically. What's next? Alex. Be on page 2 from the review. Sure. So we'll start by drawing our picture. So 0, pi over 2, pi, 3 pi over 2, 2 pi. So from pi to 2 pi are the bottom two quadrants. Consulting all silly turtles crawl, cosine is positive in the fourth quadrant. So this is my angle theta that I'm looking for. That angle's my alpha. And theta is going to equal 2 pi minus alpha, since the last axis I passed through was vertical, and theta is positive. And the alpha in this case is just going to be cosine inverse of 0.52. And then it's calculator time. Which comes, oh boy, what did I forget? I was still in degree mode from those story problems. What are we going to have to make sure we're being careful about on the test?
degree radius?
Yeah, sure do. So that comes out to be about 526. Which again, you could check, right? Cosine of 526 better give you 0.52. And 526 is between 3.14 and 6.28, right? So we're good. Mackenzie. G on page 1. Sure thing. Oh, the first G? Sure. Okay. So this one we should be using our unit circle to do. I remember that tangent is y over x. So I'd be looking for potentially a place where the y coordinate is root 3 and the x coordinate is positive 3. But I know that 3 isn't actually a unit circle angle anywhere, or a unit circle value, coordinate. So I know I'm going to have to do some reducing or something here. So remember that positive 3 is the same thing as root 3 times root 3. So I'm actually going to be looking for a place where the y coordinate has a 1 in it and the x coordinate has a root 3 in it. And then I remember here that the range for tangent is negative pi over 2 to positive pi over 2. So that's these two quadrants. In those two quadrants, tangent is is negative in that one. So we're looking for that angle theta. So I'm going to be looking in quadrant 4, where the y coordinate is 1 and the x coordinate is root 6. Or I meant root 3. Why did I say root 6? So this is the spot, right? Y coordinate has a 1 in it. The x coordinate has a root 3 in it. So I want 11 pi over 6. But remember that this should be in the fourth quadrant, or needs to be between negative pi over 2 and positive pi over 2. So that is certainly too big. So I just need to find something coterminal to it that's smaller. So if I subtract 2 pi, I'm good. Everybody, Mackenzie, are you okay with that? Yeah. Anytime you're finding an answer for sine or tangent inverse in the fourth quadrant, if you're not given a specific range for theta, you're going to have to be subtracting 2 pi when you pull that value from the unit circle. You don't have to worry about that if you're typing it into your calculator, because the calculator will deal with it. But if you're pulling it from the unit circle, you have to remember to do that. Grace? Yeah. Joe, did you have a follow-up to this?
I know that.
Oh, sure. Worksheet 4, number 8, you say? I think we have, that's this one, right? Okay. Start by drawing our picture. So we're again working from the inside out. So sine is opposite over hypotenuse. You good with that? Because 1/2 x is just x over 2 still, right? So if I do the Pythagorean theorem, we can find this b. So b is just going to be the square root of 4 minus x squared, right? Tangent theta is opposite over hypotenuse. And I don't know, did we rationalize the denominator in this answer? Or did we just leave it there? I don't know, remember what we did. Okay, so I rationalized the denominator after that. It looks like. So to get the radical out of there, we just did this. And that's as good as we can do. Is that okay? Sure. Yes, sir.
So for that one, I kind of did it differently. And
Yeah,
I
you
did
could
that
have.
So like, would that work?
Uh,
Because I got 1 minus a half x squared.
yeah, it's if you rationalize that, it's probably the same thing.
Okay, gotcha.
You might have goofed up when you squared the 1/2 x. Did you remember to make it 1/4 x squared, or do you have 1/2 x squared?
Oh yeah, that's very good.
Okay, but I mean, it's still,
Okay.
you know, like
Fourth.
the method you used is fine. You just goofed up that little piece.
I see.
And if you gave me what you gave me, I guess it's fine. You know, I prefer not to have fractions inside of fractions, but whatever. Tyler.
Worksheet 7, can you go to number 3 and just explain how you got the speed and the bearing for it?
Sure. Alex, do you have a follow-up to 8 before we move on, or do you have a... Okay, you're next then. Sound good? Okay. All right, Tyler, we're looking at number 3, you said? Okay. And you already did the work to get the final position? Can you tell me what the final position is?
It's negative 418.65 and negative 337.9.
337. Great. Okay. So the distance is just going to be like the Pythagorean Theorem.
Which one is this?
Worksheet 7. You good with that? And then to get the bearing out of this, I'm going to plot this. So this is down here in quadrant 4. Or sorry, quadrant 3.
How do we know that?
Well, it's negative 418 over negative 337 down. So I'm just plotting it on the xy axis. So my bearing is this. So 0, 90, 180, 270. And this is my alpha here. So my bearing is going to be 270 minus alpha. Just like we did on like worksheets 1 and 2. You good with that idea? And the alpha is always going to be, for these problems, the tan inverse of the absolute value of the y final over x final. So just 270 minus whatever that angle is going to give you your bearing. Is that good?
Yeah.
You don't care about what the numbers actually turn out to be, it's just the setup that you're interested in? Okay. Alex.
On page 3 of the review, can you give me the second?
Second D on page 3 from the review. Yes, I hope so. Okay. So again, we'll start from the inside and work out. This is just like a worksheet 4 problem. So I'll start by drawing my triangle. So sine is opposite over hypotenuse. So That's what my triangle is going to look like, right? And if I do sine of this, I do opposite over hypotenuse, I just get the same thing, right? That's it. So here you'll notice that we were able to kind of very willy-nilly cancel the sine inverse and the sine, and didn't have to worry about we didn't have to worry about the range. The reason we didn't have to worry about it is that we're doing it to a variable expression. So the x can handle, like that unknown part, the x, will handle the range part of it for us. So we can just cancel the signs willy-nilly if what we're like what's inside as a variable expression rather than an angle measure. Does that? Okay. Who's next? Mackenzie. Okay. So this one right here.
Oh, sorry, second. Oh, wait. Yeah, this one.
Okay. That's okay. Okay. So the thing we have to be careful about here is that since we're doing sine of and then an arc sine of, we can't just willy-nilly cancel those out because we have an actual specific angle measure given to us here, as opposed to the previous problem where it was a variable expression. So really the easiest thing to do here, Mackenzie, is I noticed that negative 98 is not a unit circle value or unit circle angle. So I'm just going to go to my calculator and take care of this. It says to give our answer in radians, so that's the only place I really need to be careful about. So this is what I'm going to do. I'm going to do my calculator degree mode, do sine of negative 98 to get that. Then I'm going to turn my calculator to radian mode and do sine inverse of that value. And that should be good. So the only thing I had to be careful about there was just the modes, right? I had to be in degree mode to do the sine of negative 98. I had to change my calculator back to radian mode to do the sine inverse of that value.
Okay, so first when you found it with degree 98 with the radians, then put that number and then
Yeah. Yeah. So there, I'll put that on there also for everybody. So just use the calculator in degree mode to get the negative 0.99. And then I put the calculator back in radian mode to do the sine inverse of negative 0.99. That gave us the negative 1.43. So that was just a calculator, like, can you understand what's going on well enough to know when to change your modes around inside of the same problem, which is kind of rude. Or not. Maybe it's a really good question. Maybe I'll ask you to have something like that on the test where you really have to make sure you understand what's going on so you can use your calculator effectively. I don't know. Who knows?
Could you do D on the same page?
Sure. This I can do purely on my calculator, since again, negative 0.34 isn't a unit circle value. And this is clearly in radians because there's not a degree symbol. So I'm just going to do tan of cosine inverse,
In radian mode?
negative 0.34, all in radian mode since I have a radian value here. I want a radian value at the end.
If it was in the degree mode, then would you switch to degree and do cosine inverse of whatever the number is, and then you do switch to radian mode and do
No, because because I want a radian value back,
Okay.
which cosine inverse in radians is giving me a radians value. I mean, if you put it in
So you want
the mode for this problem isn't going to matter because we're not actually calculating an angle at the end because the inverse is on the inside rather than the outside.
okay.
So the mode doesn't really matter, other than right here where this is clearly. Oh, no. That's just a ratio of side lengths. That's not even a radian value,
Okay.
right? That's just a number. That's not even an angle measure because we're taking the inverse of it.
Okay. So just keep it in radian.
So the mode didn't even matter in this problem. But you do it all in your calculator, whatever mode you're in, just to illustrate. So here I was in radian mode when I did that. If I change it to degree mode, I do the same thing, I get the exact same answer. And the reason it didn't matter the mode is because what we're actually calculating is a tangent, which is not an angle measure. So it's going to spit out the same value.
Oh, I see. So if it was like sine, then it wouldn't matter.
If it was tan inverse of cosine,
Okay.
the mode would definitely matter.
Okay. Gotcha. So just because it's tan or cotan.
No, because the inverse is on the inside.
Oh, okay. So the inverse is on the outside.
Then the mode definitely matters.
Okay, gotcha. But when the inverse is on the inside, it doesn't really matter at all.
Well, because you're not calculating an angle measure.
Okay, gotcha. Does it matter for the inside? Then, like whatever part the inverse is connected to. Does that make sense?
So the inverse gives you an angle, right?
Okay.
Whether you want that angle in degrees or radians, the mode of your calculator matters.
Okay.
Regular version, sine, cosine, tangent, calculate ratio of side lengths from an angle measure. Whatever your angle is measured in, your calculator mode should match.
Oh, okay.
In this problem, though, where you're doing the inverse and then calculating another function on that answer, the inverse is giving you an angle measure, right? Whether the angle measures in degrees or radians doesn't matter if it's the same angle, right? Whether it's 45 degrees or it's pi over 4, when you take the tangent of it, you get the same answer.
Okay.
That's what I'm saying.
I got you.
Who's next? Grace. 5 from worksheet 7. Okay. Let's see here. Is that this one? Oh, that's worksheet 3. Okay. 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 Let's see here. So we have the ship initial plus some wind plus some current should be the ship's final kind of speed and bearing, right? Okay. All right, let's see here. Okay. So the final bearing needs to be 114. And the final speed, it says the maximum speed is 22. No, that's not what there goes. That should be over here. Feels like I have too many variables. Let's think about this for a second. Maybe I just worded this question really awkwardly. That's kind of what I'm leaning on. Yeah, I think this is just worded weird when I wrote this thing, right? Feels like it's worded kind of awkwardly. I think that this is supposed to be here. That's what I think it's supposed to be. That's what I think is really going on. You good with that? You mumbled something, but I couldn't really hear. Right? To solve this, we have to subtract these two to the other side, right? Because that's our unknown, is the yellow. So we got to subtract the green stuff over. That's, I think, our plan. Let's look real quick at my key that I wrote and see, is that what I did? Yeah. Yeah. Okay, so I just did word things terribly. Great. All right. So for the wind, 51 degrees. Whoop. So my theta there is going to be 90 minus 51, so 39 degrees. So XW is 9 cosine 39. And my y, or my YW is 9 sine 39. And then my current is 281. It's over there. So my current theta is 169. So my XC is 13 cosine 169. YC is 13 sine 169. And then my final position, I had to do 114. So that one is, let's see, 24 minus 360, so 336. All right, let's see. So 22 cosine 336 minus 9 cosine 39 minus 13 cosine 169. Got to make sure we're in degree mode. Okay, we still are. So that's that. And then do the same thing for my sines. Sine. Okay. So 25.86 and negative 1709. And it only asks me about my bearing. So 25 over and 17 down is over here. So 0, 90, that's my alpha. So theta is going to equal 90 plus alpha, where alpha is the tan inverse of, well, I guess this is yi over xi. Oops, absolute values. So 90 plus tan inverse ABS y over x make sure I got that all in there. Yep. So 123.46. Avon.
On the review packet on page 3, did you do A or B? Doesn't matter.
Okay, we did D already.
Can you do A?
Sure. It's just a calculator problem though. So I'm going to do sine of cosine inverse 0.89. Since 0.89 is in a unit circle value, I don't have to worry about looking it up. It's just purely calculator problem. So 0.456.
Okay, I was just confused about the P saying
That means you're saving it to use somewhere else.
Oh. Okay.
Oh. So like if I did cosine inverse of 0.89, and then I could store that to say like, oops. No, I don't want to store it to x. X is a variable. I want to store it to like a or something. And then if I did sine of a, but I don't know why I wouldn't just type it all in one line on my calculator. I can always use the ANS command to use the last thing I just had, so. Anyway. I mean, you got the function, I guess you can use it. But that's all that's doing. Is that okay?
Yeah.
It's just a way to save a value for later, you know? Anybody else?
Could you go over number 5 on worksheet 3?
So we're here on top of a house. We got spying a dog chasing a squirrel. So we know that this angle is 40, and then this angle is 50. So really, I'm going to make that one 40, that one 50. And we're looking for this distance between them, right? How far apart they are. Okay. I'm going to call this y, and we're just going to end up solving a system. So I can say tan of 50 is going to equal opposite over adjacent. And that's going to give me allow me to solve for y. And then I can say tan 40 is equal to opposite over adjacent. So I can say x plus y is going to equal 20 divided by tan 40. So x is going to equal 20 over tan 40 minus 20 over tan 50. And then I'm done. Mode are we in? Still degree. Okay. By tan 40 minus 20 divided by tan 50. So Oh, shoot. I missed my subtraction symbol in there. I was going to say 400 feet apart. That is crazy. It's no longer chasing anymore. So that distance is about 7 feet. That seems more reasonable for a dog chasing a squirrel anyways. Is that cool?
Yeah.
So the biggest thing there was making sure you got your angles of depression in the right place. That's when you're drawing your picture, the most likely place you goof. Grace. Sure. Okay. Thanks for all the questions today, guys. That was really good. I think pretty productive. We're going to start chapter 5 now. Again, your test date is Friday this week, so you have another chance to ask some questions as you look over things again. But we're going to start chapter 5 today, and we'll do some more chapter 5 on Wednesday. Okay? Felt better than just like going straight into a test. You know what I mean? All right. So chapter 5 is kind of about, we're going to start talking about these trig identities. And then when we say an identity, what we're really talking about is something, it's like an equality statement that's kind of true regardless of the values that we're choosing. So we'll start with a few basic ones that we're already kind of aware of. So the first ones that we'll talk about are these reciprocal identities. So we know that for sine, cosine, and tangent, they have reciprocals, cosecant, secant, and cotangent. So I know that, for example, sine is equal to the reciprocal of cosine, or cosine is equal to the reciprocal of sine. That cosine is the reciprocal of secant, or secant is the reciprocal of cosine, or tangent is the reciprocal of cotangent, or cotangent is the reciprocal of tangent. Similarly, we have two what we call quotient identities. So remember on the unit circle that tangent is equal to y over x, right? And on the unit circle, the y coordinate is sine and the x coordinate is cosine. So if we put that together, then tangent is equal to sine over cosine, right? Tangent is y over x on the unit circle, and y is sine and x is cosine, then tangent is sine over cosine. And if cotangent is the reciprocal of tangent, cotangent has to be equal to cosine over sine. Everybody's okay with that? Feel okay? So if we think back to our unit circle here, So our next identity, if I pick any point on that unit circle, we can say that the Pythagorean theorem holds that x squared plus y squared has to equal r squared. Everybody agree with that? And on the unit circle, x is cosine, y is sine, and the radius is 1. So this just boils down to cosine squared plus sine squared is equal to 1. Now notice here that the common notation, rather than putting a parenthesis around the whole thing and then the squared, is we put the squared in between the trig function and the variable. That's the common notation that we'll use to represent that rather than the two sets of parentheses for clarity's sake. Because if you don't put the two sets of parentheses there, it's unclear whether you're squaring your theta and then doing the cosine of it, or you're doing the cosine of theta and then squaring your answer. We mean the second one. To kind of make sure we're clear about that, we're going to put the squared next to the cosine rather than next to the theta. Is that okay for everybody? If I take that, then I can manipulate this. So if I divide both sides of this equation by cosine squared, cosine squared divided by cosine squared is 1. Sine squared over cosine squared, well, sine over cosine is tangent, right? So if I have sine over tangent, or sine over cosine times sine over cosine, it'd be tangent times tangent. So tangent squared, right? Everybody's okay with that idea? And in a similar fashion, if I have 1 over cosine squared, I know 1 over cosine is secant. So 1 over cosine squared is going to be secant squared. And similarly, if I had divided this by sine instead, or I should say sine squared, excuse me. Cosine over sine is cotangent. So cosine over sine, or cosine squared over sine squared is cotangent squared. Sine squared divided by sine squared is 1. And 1 over sine is cosecant, so 1 over sine squared is cosecant squared. And we put these all together, and these are what we call our Pythagorean identities, since these are all based on the Pythagorean Theorem. Now, one other thing you might have noticed when looking at the unit circle, if I did sine of 30, I get 1/2. And if I do cosine of its complement, cosine of 60, I also get 1/2. You guys notice that on the unit circle? No? Well, that's something that's true. So these cofunctions identities, summarize that. So sine of pi over 2 minus theta is going to be equal to cosine. So if I look at the complement of theta and do the cosine of that, it should be the same as sine was. And if I do the same thing with cosine, if I take cosine of a complement, that should be sine. And then tangent and cotangent have a similar relationship. Those are cofunctions. And secant and cosecant are also similarly related. And then our last set of identities are called the odd even identities. So recall that when we looked at the graph of sine, that we noted that sine was an odd function. So since sine is an odd function, we know f of negative x is equal to negative f of x. We noted that cosine was an even function. So f of negative x has to equal f of x. We noted tangent was an odd function. So f of negative x has to equal negative f of x. And then obviously the reciprocals had to be the same, right? So cosecant was an odd function. Secant was an even function, and cotangent also an odd function. I'd like to point out to you that if you look in the content library, I've condensed these into one place and typed them out nice and neat for you. Everybody's okay with that as well? So there's all the identities in one place that we just kind of discussed and went through all together, all in one place. We'll stop here with just a few minutes left before we get into anything else. We'll do some examples of things tomorrow or next time. Don't forget about the test is what day? Friday. And the homework set for this week is just the rest of the Chapter 4 stuff. Any Chapter 5 things that we assign are going to go into the problem set for the week after. Everybody cool?
Yeah.
Because this is the first section of Chapter 5, yes.